Um, so today I'm going to talk about a holistic approach to particle flow reconstruction in imaging neutrino detectors using machine learning. And so before I dive into the subject, I'd just like to point out that the work that I'm going to be presenting today is a collaborative work of many people at SLAS that are dedicated to developing machine learning techniques, and in particular in developing these techniques for data reconstruction in liquid argon type projection chambers, which has many applications to some of the current experiments, such as microboots, but also future experiments such as the short baseline neutrino program and also the DUNE experiment. I understand this is not exactly dark matter experiments, but I hope that some of the techniques that I present today will have some use to you and to your community. And so the group that I work with consists of 3 scientists, 3 postdocs, and 3 grad students that are all pictured here and have contributed to what I'm going to show today. And so just to set the stage, the kind of data that we are dealing with in liquid argon TPCs is what you can see on the bottom left corner here in this slide. Here, what you have in this image is you have a neutrino interaction in the detector, and you've got several tracks and a shower emanating from the interaction vertex. And you can see that the kind of data you're looking at is highly granular. It gives you the energy deposition in different voxels in the detector, and it's very precise. And what you're trying to extract from this kind of image is very high-level information about the neutrino. So you'd like to know the neutrino type that interacted, electron neutrino in this case. You'd like to know the kind of interaction that the neutrino underwent, in this case, a charge current interaction. And you also like to know the amount of energy that the neutrino is carrying. This is all you need to do some oscillation physics. And so because your data presents itself in the form of an image, it's natural to want to use a convolutional neural network because this is the traditional method of analyzing an image. And you can very well just put the whole image through the network and just extract high-level information such as neutrino type and energy. The potential issues with this method is that, of course, very rarely does your neutrino image manifest itself by itself in the detector. It's typically overlaid with a bunch of cosmic rays, or it's also piled up with other neutrino interaction. And so you need to be able to at least identify which energy deposition are associated with the neutrino interaction and try to cluster those together before you can even think about putting the image through a convolutional neural network. The other issue is that because the images are so granular, the phase space that you have to cover to try to train something like this, which is essentially a huge single step of information reduction, is very large, and so that's very tricky. And also, if your network gives you the wrong answer, so it tells you that, for instance, this neutrino that interacted is a muon neutrino, it's very hard to reverse engineer what went wrong in the network and why it thought so. And so we believe there's a better way of engineering a reconstruction chain, which is to enforce the extraction of hierarchical physics feature. So we start with the image in the bottom left corner, and first we try to extract the pixel level, low level information. So one of the things we'd like to know, for instance, which we know is useful for the reconstruction, is to distinguish for each of the energy deposition in the image, which class of particle the energy deposition belongs to. So for instance, here, what we represented in step 1 is that the pixels that belong to tracks have been colored in the orange color, and the pixels that belong to showers have been represented in the cyan color. Another thing that we'd like to know at the pixel level is where are interesting points. So for instance, where are the endpoints of tracks, and where are the start points of shower fragments, for instance. And then once we have done this first step of the reconstruction, we can leverage the information that we've extracted about the particle type, for instance, to try to distinguish within each particle type how many instances you have. So you can see here we've got a bunch of voxels associated with tracks, but we know there are more than a single track instance, and we'd like to be able to distinguish those. What we'd also like to be able to know is if you have several shower fragments, such as in this image, you'd like to know if this fragment actually originates from this fragment. So if there's a parentage connection between them. And if it's the case, you'd like to be able to put them into a single particle instance. And also at this stage, you can try to identify which of the interesting points you've identified at the previous step actually corresponds to a vertex where several particles originate from. And then once you've been able to distinguish the different particles together into separate groups, you actually can leverage the information from the colorimetric information of the detector to do particle identification, and also to do energy reconstruction of the different particle components. And then at this stage, what you do is that you take the different particles in your image and you try to cluster them into interactions. So in this case, it's trivial because all of the particles come from a common interaction. But as I mentioned earlier, this is rarely the case. You often have background and also other neutrino interaction involved in a common volume. And at this stage, it's also important to note that the whole chain here is made of different steps which involve a neural network. And so you can chain these different steps of the reconstruction together and optimize them together, which is a very useful feature. And so I mentioned that one of the first reconstruction steps is to try to do pixel feature extraction. And for those of you who have tried to do this task before, you'll be familiar with the architecture that is commonly used to do semantic segmentation, which is UNet. And the UNet architecture is a convolutional neural network which presents itself schematically like this. So you've got two crucial parts. You get an encoder and a decoder. And at each of these encoding steps here, as you go deeper into the network, we use strided convolution to reduce the spatial size of the image progressively to a very low resolution image. And the reason why this is useful is that you can extract features at different scale of the image. And then what you do is that you use a transpose convolution to get back to the original resolution of the image. What's important to note as well is that we've got these skip connections, which essentially propagate the information at each of the depth level. And the reason why this is useful is that this allows the network to retain the spatial information. So it doesn't have to learn that. It just has to learn features that are interesting to do, for instance, semantic segmentation or any other task that you're trying to do. And if you want more detail about the architecture, please check out this paper. I should mention that there are particularities to this UNet that we use. One, that we use residual connection instead of just simple convolution. And we also use sparse convolution. So we only do convolution essentially on active sites in the original image. And this is particularly crucial for liquid argon TPCs because our occupancy in our 3D images is typically 10 to the -4. So it means that for every active voxel, we've got 10,000 non-active voxels. So it would be incredibly computationally expensive to do convolution on empty sites, and also doesn't add any information. And so the first use that we make of this USNet that I just described is to try to classify the different energy deposition that you get in the image into different particle classes. Typically, what you're trying to predict is which pixel belong to showers, minimum ionizing particle in the dark blue here, delta rays in the green, Michel electron in the yellow, and finally protons in the dark red. And so on the next slide, what I'm showing is the performance of the network by showing the voxel classification accuracy for each of the 5 classes that I just mentioned. And what you can see is that for the classes that are most represented in our data set, namely minimum ionizing particle and showers, the accuracy is very high. It's above 99%. And of course, having a network that gives you particle classes so accurately is very useful, because if you want to do clustering, for instance, instance clustering downstream, it's very useful to be able to do instance clustering on separate classes instead of having to do it on the whole image. And so this is something we can leverage downstream. If you want more detail about the performance of this network, including confusion matrices, etc., please check out this paper that I'm referencing here. The next thing that we'd like to extract at the pixel level using our USNet is what we call interesting points. And so these are the important points of the image, such as endpoint of tracks and start point of showers. And so we reuse this USNet architecture as a feature extractor. And what we do is that we add a parallel path to the decoder. And these parallel paths contain different layers, which we call PPN1, PPN2, and PPN3 here. And what these do is that they actually make proposal about where the point should be in the image. And so you start with the lowest resolution image, and you try to predict the mask of where interesting points are in this lowest resolution image. And so if you map these predictions at the lowest resolution back to the original resolution, this actually corresponds to a region proposal, which is what you can see here represented in this image. So you can see the network has put boxes where it believes there are interesting points in the image. And then you use another PPN2, which you extract features on the intermediate resolution here to narrow down this prediction. And then finally, you use the features extracted at the original resolution to narrow down the prediction down to an exact point in the image. And so on the next slide, I'm just showing you a realistic example of actual prediction that the network has made. You can see that at the lowest resolution, the region proposal is actually already identify where we expect to have interesting points. So you can see there are boxes at the endpoint of tracks and boxes at the start of showers. And then at the intermediate resolution, we simply narrow down the position of these boxes. And finally, at the original resolution, we get exact points of where the points lie in the image. And what's interesting to see is that if you look at the distance from a label point that you're trying to predict to the closest predicted point by the network, you see this orange histogram on the left. And you can see that the distance between those points is typically less than a voxel. So not only does the network give you the correct voxel, it actually tells you where exactly the point lies within a voxel. If you look at the fraction of predicted pixel which are within 10 pixels of a true label point that you're trying to predict, you can see that this figure is 98%. So this means that the network is very efficient at finding points where we want it to find points. Again, if you want more detail, please check out this paper. Finally, the last thing that we're trying to get out of the image at the pixel level is what we call dense clustering. And the idea at this stage is that for each of the different classes that I've mentioned earlier, we would like to be able to distinguish different instances of the class within the class. So for instance, if you've got different tracks in your image, which typically we do, you would like to be able to separate these tracks into different objects. And so the way that we do this is that we use this UResNet feature extractor that I mentioned earlier. And instead of using it to do classification, we use it to learn a mapping, which is essentially a function, which maps the position in Euclidean space of the points in the original image to another space, which we call embedding space, in which the points that belong to a single instance are actually clumped together. So as you can imagine, you can have several tracks in the original image that touch, for instance, and so it's tricky to cluster them together. But once you map them to a space where they are clumped together like this into spheroids, then it's easier to cluster them together by using, for instance, Gaussian kernel. The challenge with that is that you don't know how many clusters you have in your image, and you also don't know their spatial extent in the embedding space. And so we get the network to actually learn an extra two things, which we call margin and seediness, which gives you the position of where the centroid of the Gaussian kernels are in your embedding space, and also gives you their spatial extent. And so with this information, we can actually do clustering in the embedding space and map that back to the original space. And so let me give you a quick example. On the left-hand side, these are the fragment instance label in the image. So you can see here, you've got separate tracks that touch each other. And you also here have a shower. And you can see that at this point of the reconstruction, we're just trying to put the dense fragment of the shower together into instances. We're not trying to put the whole thing together. What's interesting to see is that if you take these two tracks, the green and the red, and you look at where the network mapped them in embedding space, you can see that this corresponds to the yellow and to the blue clusters here. So even though they touch in the original space, they are well separated in embedding space. And then you use this margin and seediness as we predicted to make Gaussian kernels in your image, and you map back the clustering back to the original space. And you can see that the predictions are very close to what we're trying to predict. If you look at the performance of this clustering algorithm more systematically, we use typically clustering metrics that we call purity, efficiency, and adjusted rand index. So we'll just ignore SBD for now. And what purity represents is a measure of overclustering. So if you have two separated label tracks and you put them together, then the purity goes down. So we want the purity to be close to 1. And efficiency, conversely, is a measurement of underclustering. So if we have a single label track and we break it down into several tracks, then your efficiency goes down. So we want that to be close to 1 as well. And adjusted rand index is a very common thing to use to characterize clustering. It's actually a measurement of the similarity between two different partitions of a set of points. And you can see that if we look at the average adjusted rand index for a given image in our simulated data set, we get an average RI of 97.3%, which is a very high value. And so I recommend that you check out this paper if you want more metrics and detail about how this algorithm performs. And so at this stage of the reconstruction, what we have is that we have a set of tracks and we have a set of these shower fragments. And what we'd like to do at this point is to put these fragments together when they have some parentage relation between them. And so doing that using a convolutional neural network is usually very challenging because, as you know, convolutional neural network have a receptive field. And so if two fragments are very distant from each other, which they very well can be in the case of showers, then it's tricky to put them together using a CNN. And so what we do instead is that we use a graph neural network. And the idea here is that each of the shower fragments that we've obtained from the previous reconstruction step essentially represent a node in a graph. And then we make connection between these different nodes in the graph. And then we use a process called message passing, which essentially allows us to update the features of the edges and also the features of the node in the graph. And this is an iterative process we can repeat. And of course, the functions that update the node and the edge features are neural networks, so they are learnable functions. And then what we do is that we use the edge features that we've developed in the network to constrain the connectivity graph. So we can use the connections that the network are making between the different nodes to actually group the nodes into separate groups. So here, this is what this example shows. We've been able to cluster the fragments into two separate showers. And then we leverage the node features that the network has extracted to actually try to identify the shower primaries. So which of the shower fragments in each shower group actually initiated the shower. So which essentially shower fragment came first. And so this was just an overview, and now let me go into a little bit more detail about each of the different steps. So here I'm showing you the kind of input we get to the graph neural network. So this is what comes from the previous reconstruction chain. Here you're just looking at the energy deposition associated with electromagnetic particles. And you can see that each of the dense fragments has been labeled into a different color. And what you're trying to do is to put these fragments together into groups. And so the first step is to extract features out of these fragments. So typically we just take a set of summary statistics of each of the fragments. We take the centroid of the fragment, we take the covariance matrix and the PCA, and we also get the start point and an estimate of the direction of the fragment from the point proposal network. And so what the network sees at this stage is not a detailed view of each of the fragments, but just a set of summary statistics, which you can picture as being some sort of ellipsoid in space. And then what you do is that you make connection between the shower fragments. And typically what we do is that we build what is called a complete graph, which means that we connect every fragment with every other fragment in the graph. And so we allow every fragment to talk to every other fragment. And so we also give features to the edges, which we know might be useful to constrain the connectivity graph. And essentially what these edge features contain are variations of the displacement vector. So this corresponds to essentially the distance between two fragments. So schematically here on the right-hand side image, you can see that these two fragments are distant from each other. The edge that connects them is a lighter color. And if two fragments are close to each other, the edge is a darker color. And so at this stage, we do what is called message passing in graph neural networks. And the idea here is that we update the edge feature and the node features. And we update the edge features by taking a function of the features of the nodes that the edge is connecting together. So if you have this edge connecting I and J, you take the features of the edge and the features of the two nodes that it connects. And to update the nodes, what we do is that we build what are called messages. And messages are essentially a function of the features of the node that is communicating the message and the edge that is carrying the message. So if this node is communicating a message, you take the features of this node and of the edge that connects it to this node here. And then to update the node feature, yeah?
Just 5-minute warning.
Okay, thank you very much. And to update the node features, what you do is you take a function of the node features of the previous step and some aggregation of the messages that are coming to this node from adjacent nodes. And so after repeating this process 3 times, you can do edge binary classification. And what you're trying to predict is that if an edge connects 2 nodes that belong to the same group, you'd like the network to predict this edge to be on. And if it connects 2 nodes that belong to separate shower groups, you'd like the network to predict this edge to be off. And so if we actually apply this technique to an actual image, this is the kind of thing you can get on the right-hand side. And what you can see is the network has mostly done a very good job. So it's connected the things that are supposed to be connected. But it's made a single mistake. So it's connected these two nodes together, even though they shouldn't be connected. But it's important to note, so at this stage, if we just use the score and say that if an edge has a score above 0.5, we just connect these elements and put them into the same group, you can see that having this mistake will put these two nodes and these three nodes together into one group. But what you can also realize at this stage is that these two nodes, for instance, the edge that connects them is below 0.5. And if you take these two nodes, the edge is also below 0.5. So the network is mostly considered these two shower groups should be separated. They just made a mistake. And so if you actually try to minimize the loss of a certain partition, instead of just thresholding on the edge core, then you can recover the correct grouping of the edges. Here, I don't have I don't have any more time to go into detail about this procedure, so I'm just going to skip this slide. But essentially what you get is what you see here on the right-hand side. And you can see that even though the network had made a single connection here mistake, we have been able to recover the correct grouping by minimizing the loss. And what you can also see, which is interesting, is that the edges that the network has selected actually look sensible. And so if you look more systematically at the performance of this clustering algorithm, you can see on the left-hand side the distribution of the clustering metrics that I've defined earlier, adjusted rand index, purity, and efficiency. And what you can see is that on average for a given image, the purity and efficiency is roughly 99.5%, and the ARI close to 98%. So it's doing a good job at separating the different shower objects. And at this point, also, it's important to remember that there's another task that we are trying to achieve, which is to predict which of the shower fragments are primaries. And so you can see on the left-hand side the distribution of the score for true secondary fragments and true primary fragments. You can see that for true primary fragment, the score is very close to 1, and for true secondary fragment, the score is very close to 0. On the right-hand side, you can see an example where the nodes that have a score close to 1 have been represented in red, and you can see the network has done a good job at identifying the shower starts here. And typically, when we do shower primary prediction, what we do is that we take the predicted groups that we get from the parallel task, and we pick the shower fragment that has the highest primary score. And if we do so, we actually get the correct primary almost 100% of the time. So it's doing a very good job. Okay, so the final task that I want to mention is this interaction clustering. So at this stage of the reconstruction, we've got different tracks coming out of the dense clustering, and we've got different showers coming out of the graph neural network. And so what we would like to know is that if different showers and tracks actually originate from a common vertex and actually correspond to a single neutrino interaction, we'd like the network to be able to cluster them together as one. And so what we do is that we leverage the graph neural network that I presented earlier, but instead of trying to put fragments together into particles, we try to put particles together into interactions. So we'd like the network to say that an edge is on if it connects two particles that belong to the same interaction. Of course, this is crucial to separate the signal from the background and also to resolve neutrino pileup. On the left-hand image here in this example, you can see what we're trying to predict. So we want the network to put these different objects together into one interaction and these two into another interaction, and also to be able to distinguish these cosmic rays as not belonging to either of those. And on the right-hand side, you can see the prediction that the network has made, and you can see that it's done a good job at clustering the different particles correctly. If you look again systematically at the performance of this network, you can see here the average ARI efficiency and purity as a function of the number of interactions. Just to give you an example, in this right-hand side image, we've got 7 interactions. So there's 2 neutrino-like and 5 cosmic-like interactions. And so if you look at the corresponding bin, you can see the average ARI efficiency and purity are all above 99%. So the network is doing a good job at interaction clustering. So at this point, I'd like to conclude. Of course, we need a state-of-the-art reconstruction chain to achieve the goals of the short baseline neutrino program and DUNE, which are experiment that will come online in the near future. And we believe that to achieve this goal, it's good to have a completely open source development. So we have an open data set, we have an open source code, we have an open software container which supports this source code. And so we have a completely open collaboration. You can follow the different links if you want access to these different things. And if any of you is interested into knowing more detail or in participating in the effort, please don't hesitate to contact us. And so I hope that this talk has demonstrated that a machine learning-based hierarchical feature extraction is very successful to achieve this goal. And essentially what I presented today is that we use basically two basic neural networks to do the different tasks that we're trying to achieve. One that is a pixel feature extractor, sparse URSNet, which gives us semantic segmentation, point proposal, and dense instance segmentation. And then we use graph neural networks to cluster distant objects together. So typically clustering shower fragments together into shower groups, and also clustering particles together into interactions. And so for our future goals in the immediate future, we'd like to extend the reconstruction of the particle clustering to particle flow. So we'd like to know the ordering of the particles into an interaction. We'd like to also do energy reconstruction and interaction vertex reconstruction. In the longer term, we are interested in looking into model uncertainty estimation, systematic uncertainty propagation through neural networks, and also studying domain discrepancy. So trying to mitigate the differences between data and simulation. And with that, I'll just leave you with my summary slide, which shows the different steps of the reconstruction and their respective performance. Thank you very much.
Thank you, François. That was a very nice talk. So now we have a little bit of time for questions. Chloe, would you go ahead and read the top voted question? And François, if you want to take a look at the list of questions, you can follow the link I just put in chat, or you can just listen to what Chloe says, as you prefer.
Yeah, if you share the link, then others can see. But yeah, we only have a minute or two, so.
Sure. So right now, our top voted question is, can you share your experience on debugging large architecture like yours? Do you use any weight/gradient visualization techniques?
Optimizing which thing? I'm sorry, I didn't catch that.
Experience on debugging large architecture, and do you use any weight and gradient visualization techniques?
I'm sorry, I don't understand the question. Debugging? I need to see is the question on Zoom?
If you click the link in that was posted in the Zoom chat, it'll take you to the question. I think it's just, I didn't write it, but if they're big architectures, how do you visualize it? I think that's the question. But if someone,
or if you don't mind to chime in, I will just chime in, François, while you're putting up the link. I think one thing you do, and some people in our group does, is, for example, like to check the, if something's not training, then you have to go check the activations. I don't think we typically do look at the feature maps, because that not necessarily really tell us something is very specific. But activations to check the gradient, the level of the gradient at different stages, that's definitely important. Maybe François can point out other things if you remember. I mean, other things such as, how labels corrupted and such things like that, maybe.
Okay, I'm sorry, I'm still pulling up the question. Okay. Yeah, I mean, I think like Kazu said, we don't actually dig into trying to look at the feature maps very much. Typically, we just try different things and see what improves the performance of the network. I can mostly speak about what I've worked on, which is the graph neural network that I've presented, for which many different things have been tried. So I just showed the one that works best, but we tried many different ways of doing it. So we tried different ways of encoding the features of the nodes, for instance. We tried different ways of implementing an input graph. We tried different way of doing the message passing. There's many things you can play with and just try to see and get a sense of what actually works for you. And this is the way we've approached it, at least for this part of the reconstruction.
Okay, we have time for one more question. So the next top voted question was, what framework, TensorFlow, PyTorch, Custom, did you use to implement the graph neural network?
Yeah, so the graph neural network is completely PyTorch. That's right. And we re-implemented, we use essentially the message passing function that I mentioned, which is a meta layer to do the prediction that I've shown.
Great. Thank you very much,
And
Francois. I think
can we
should.
just,
Oh, go
just
ahead.
since I'm particularly curious, can we just quickly do this last question? Though I didn't write it. What was your motivation for using the graph neural net over other possibilities? What advantages does it bring? Really short.
Oh, so, well, yeah, okay. So we saw that we were really struggling to do clustering of distant objects using CNNs. And so we believe that GNN are particularly appropriate to do this kind of clustering because they can see contextual information from different fragments and put them together. So if you extract something like the fragment direction, we know that the graph neural network will be able to correlate these things together, even if they are far away from each other. If they are somehow correlated in angle, this is something that the network can use.
Thanks.
Thank you, Francois.
Thank you.
Looking forward to more discussion on this and breakouts. Okay, why don't we move on now?